This is the second part of our discussion about waves. In this part, we are going to learn about interference and standing waves. Interference of waves. Two waves can be at the same place at the same time, so they can superimpose and then they can create a new wave, and this is called interference of waves. For example, in this diagram we have two waves. Assume they have the same amplitude and same frequency, and you can see that the two waves have the same phase. So these two waves are in phase, and when they interfere, they can create a wave with a larger amplitude. If the initial waves have the same amplitude, the amplitude of the new wave will be twice that of the original waves. This type of interference is called a constructive interference. On the other hand, if the two waves are out of phase and at the same time assuming they have the same frequency and amplitude, when they interfere, they will destroy the two waves and there wouldn't be any wave. So this type of interference is called a destructive interference. Path difference is given by this symbol delta. Let's assume that we have two sound sources S1 and S2, and P is a point in space, and P is at distance L1 from S1, and at the same time distance L2 from S2. When two sound waves interfere at point P, which are coming from source S1 and S2, and they travel two different distances. And if we assume that the two sound sources are in phase, then the path difference delta is L2 minus L1, basically the difference between the two distances. But if the sound sources are out of phase, then the path difference is L2 minus L1 plus 1/2 of the wavelength. So the total path difference is L2 minus L1 plus lambda over 2. So the important condition is whatever this path difference, if path difference is an integer multiple of wavelength, you receive the two waves at point P in phase. So when point P receives the two waves in phase, that creates a constructive interference. So this M could be 0, plus or minus 1, plus or minus 2, or plus or minus any integer value. On the other hand, this path difference is M plus 1/2 wavelength. Then it becomes a destructive interference. Again, M could be 0, plus or minus 1, plus or minus 2, and so on. And these are the two conditions that tells us whether the interference is constructive or destructive at a given point in space. Now in nature, we normally don't see constructive interference or destructive interference. The reason is, most sound sources emit sound with changing phase difference. Phase difference in nature changes very rapidly, so that we can see clearly or we cannot hear is a constructive or destructive interference because it changes so rapidly, so we don't see that effect. In order to see a constructive or destructive interference, we need two coherent sound sources. Coherent sound sources are the sound sources that emit sound at constant phase difference. In general, it could be sound, it could be any other wave. In general, coherent sources emit waves at constant phase difference. Then the two sources are called coherent sources. Normal sources that emit waves are not coherent sources, so we cannot see interference. So the condition is sound sources must be coherent to produce a constructive or destructive interference continuously at a given point. An example, two speakers A and B emit sound at the same phase. Point P is 20 meters from A and 36 meters from B. Can a person standing at point P hear a large sound or any sound at all? The wavelength of sound is 6.4 meters. So the question is, the person at P can hear a large sound or any sound at all. So large sound means a constructive interference. So we need to determine whether the person at point P experiences a constructive or destructive interference. To answer the question, we need to find out the path difference, which is 36 minus 20, which is 16 meters. Since the two sources emit sound at the same phase, so there is no phase difference, no lambda over 2 term here. So the condition for constructive interference is m lambda equals to delta. So what we are trying to do is trying to find a value for m, which is delta over lambda. If this m is an integer, it's a constructive interference. If this value is an integer plus a half integer, then it's a destructive interference. So let's try to find that value m. So delta is 16, lambda equals to 6.4. By dividing 16 by 6.4, we get 2.5. So this is not an integer, so it's an integer plus a half integer, so which is a destructive interference. So m is not an integer, so it's a destructive interference. So person cannot hear any sound at P. Beats. Beats are also a result of interference. When two waves with slightly different frequencies interfere, one can hear that the sound intensity increases and reaches a maximum value. Then it decreases and then it increases again, reaches a maximum value. So intensity changes with time. But this change repeats after a fixed time interval. This frequency, this repeating frequency, is called the beat frequency, and that frequency is given by the difference between the two frequencies. If you have two sound waves with frequency f1 and f2 which are only slightly different, we can see a beat frequency of f1 minus f2. We have this absolute value sign. That's because we don't know which one is greater. So the beat frequency is the difference between the two frequencies. An example, when two tuning forks A and B are sounded together, 3 beats per second could be heard. If FA, which is the frequency of A, is 320 Hertz, find the frequency of B. So the equation is absolute value of FA minus FB equals to 3. So FA minus FB could be either plus 3 or minus 3. So we don't know which one is greater. So we need to consider both possibilities. So FB equals to FA minus or plus 3. FA is 320. So 320 minus 3 or plus 3, which is 323 or 317. So we cannot give an exact answer. What we can say is it could be either 323 Hertz or 317 Hertz. The second part is standing waves. Let's assume we have two waves traveling in opposite directions, but they have the same amplitude and same frequency, but they can interfere. So when they interfere, it creates a wave which we call a standing wave. The reason is this wave does not propagate, but it's just an oscillation, and the amplitude of the oscillation depends on the location in space. So the amplitude changes from point to point on the wave. The equation of such a wave is given by y equals 2a sine kx times cosine omega t. So y is the displacement at any given point on the wave, and you can see that cosine omega t term, omega is the angular frequency, but this term is multiplied by a factor 2a sine kx. Normally we know that this factor is the amplitude. Now this means the amplitude is 2a sine kx, but since the sine kx term, the amplitude is a function of x, which is the position. So the amplitude is a function of position, and it changes from position to position. An example for standing waves is standing waves on a guitar string. Standing waves on strings. There are two situations that we can consider. One would be a string that are fixed at both ends. The second situation is the string that is free to oscillate at one end, but the other end is fixed. Let's first consider where the situation both ends are fixed. When both ends are fixed, the string oscillates at different modes. One of the ways that the string can oscillate is this first diagram. The points that are not oscillating are the points that are fixed to the ends. So these points are called nodes. And then you can see at the center it has the maximum amplitude. So the points with maximum amplitude are called antinodes. This is for the first possible mode on the string, and we call it the fundamental mode or the first harmonic. So the second mode is something like this. You have a node at the center and also nodes at the end, and there are two antinodes. So this is called the second harmonic. And the next higher mode would be this one. Basically, if you consider in terms of loops, the first harmonic has one loop, the second harmonic has two loops, third harmonic has three loops. And if the length of the string is L, we can relate that length to the wavelength, because one loop is 1/2 of a wavelength and two loops are equal to one single wavelength. And three loops are equal to 3 times of 1/2 of a wavelength. So we can write that as an equation. L equals to lambda over 2 for the first harmonic or the fundamental, and L equals to lambda, which is also equal to 2 times lambda over 2 for the second harmonic, and L equals to 3 times lambda over 2 for the third harmonic. So if you look at the relationship between each one, you can say for the nth harmonic, we can say that L equals to n times lambda over 2. So that gives us an equation for the wavelength. So the wavelength of the nth harmonic is given by 2L over n. So this n could be 1, 2, 3, or any positive integer number. And n equals 1 represents the fundamental mode or the first harmonic. N equals 2 represents the second harmonic. N equals 3 represents the third harmonic. Then we can also obtain an equation for the frequency, because frequency is equal to the velocity divided by the wavelength. So the frequency of the nth harmonic is nv over 2L. And n could be 1, 2, 3, and so on. The other possibility is one end is fixed and the other end is free to oscillate. So in this situation, the other end, the end that is free to oscillate, is always an antinode. But the fixed end is always a node. So the lowest possible mode is the first diagram, which has an antinode at the right end and the node at the left end. So if the length of the string is L, this is 1/4 of a wavelength, because this is 1/2 of a loop. One loop is 1/2 of a wavelength, and this is 1/2 of a loop, which is 1/4 of a wavelength. So L equals to lambda over 4 for the fundamental or the first harmonic. The second harmonic would be a loop plus 1/2 of a loop. So we have 1, 2, 3, 3/4 here. So the length of the string would be 3 times lambda over 4. And the next harmonic, the third harmonic, would be 2 loops plus 1/2 of a loop. So we have 2, 4, 5. So we have 5/4 of wavelength. So 5 lambda over 4 for the third harmonic. So we can write a general equation for the nth harmonic. L equals to 2n minus 1 times lambda over 4. So the wavelength of the nth harmonic is 4L over 2n minus 1. So n is equal to 1, 2, 3, 4, and so on. Same way, the frequency of the nth harmonic is equal to 2n minus 1 times v divided by 4L. We discussed the waves on strings. Same way we can discuss the waves on air columns or in tubes. For that, also there are two possibilities. One is when the both ends of the tube are open. The second situation is one end is closed and the other end is open. So let's consider the situation that both ends are open. So when both ends are open, there will be two antinodes at the ends. Open ends will always have antinodes. So the first possibility is two antinodes at the ends, and then there is a node at the center. So we know that this 1/2 of a loop is chord of a wavelength. In the fundamental mode, then we have 2 times lambda over 4. This part is lambda over 4, that's lambda over 4. So 2 times lambda over 4, which is lambda over 2. The next higher mode would be a loop plus 2 half loops. So that would be 4 times lambda over 4. This 1, 2, 3, 4. And that's equal to 2 times lambda over 2. And the third harmonic would be 2 complete loops plus 2 half loops. So it's 2, 4, 5, 6 quarters, or 6 times lambda over 4. So that's 3 times lambda over 2. Now we can see the relationship is 1 times lambda over 2, 2 times lambda over 2, 3 times lambda over 2. So for the nth mode, n times lambda over 2. From that, we can write the wavelength of the nth mode, which is 2L over n, and the frequency of the nth mode is NV over 2L. Now consider the last possibility. One end is closed and the other end is open. The open end has an anti-node, and the closed end will have a node. So the first harmonic, or the fundamental, will have only 1/4 of a wavelength. So the length would be 1/4 lambda over 4. And the second harmonic would have a 1 full loop plus 1/4, so which is 3 times lambda over 4. And the third harmonic will have 2 full loops plus 1/4, so that's 5 times lambda over 4. So this way we can write for the nth mode, which is 2n minus 1 lambda over 4. So the wavelength of the nth mode is 4L divided by 2n minus 1. And the frequency of the nth mode is 2n minus 1 V over 4L. And n equals to 1, 2, 3, 4, so on. Now let's go over an example. A string is clamped at both ends. The tension of the string is maintained at 12 newtons. The fundamental frequency of the standing waves on the string is found to be 90 Hz. The length of the string is 2.4 meters. A. Find the wavelength of the fundamental mode. B. What is the speed of the wave? C. Find the frequency of the 7th harmonic. D. If the tension is doubled, what will be the new fundamental frequency? To answer the first question, find the wavelength of the fundamental mode. Since the string is clamped at both ends, this is the diagram for the fundamental mode. We know that this is 1/2 of a wavelength. So the length is 1/2 of lambda. So the lambda is 2 times L, it's 2 times 2.4, which is equal to 4.8. So I didn't use the formula for lambda n. You can use that too. In that formula, n equals to 1, and that will give you the same value. B, to find the speed of the wave, we know that speed is f times lambda. F, or the frequency of the fundamental mode, is 90 Hertz, and the wavelength we found at 4.8. So the speed is 90 times 4.8, which is 432 meters per second. And the third question is to find the 7th harmonic, frequency of the 7th harmonic. The formula for the frequency for the nth harmonic is NV over 2L. For the 7th harmonic, n equals to 7. So 7 times V is 432 divided by 2 times 2.4. So the frequency of the 7th harmonic is 630 Hz. The last question is to find the fundamental frequency if the tension is doubled. The previous velocity is 432, which is equal to square root of t over mu. But you can see that if we change t, that changes the speed. So first we need to find v before finding the fundamental frequency. Now the new speed would be square root of 2t over mu because t has doubled. So we can write that as square root of 2 times square root of t over mu. But square root of t over mu is the old speed or the velocity, which is 432. So the new speed would be square root of 2 times 432, which is 610.9 meters per second. So the new fundamental frequency F1 is v over 2L. This v is new speed, which is 610.9 divided by 2 times 2.4. So that's 127.3 hertz. The second example, a uniform glass tube has one end closed, the other end is kept open. An audio signal generator is used to resonate the air column in the glass tube. It is observed that the frequency of the second harmonic is 514.5 Hz. Question A, find the length of the tube. Question B, what is the fundamental frequency? So the second harmonic is given. This is the diagram for the second harmonic of a tube when one end is closed and the other end is open. We have 1/2 plus 1/4, so 3 lambda over 4 wavelengths, and that's the length of the tube. So length is 3 lambda over 4, so lambda equals to 4L over 3. But lambda is not given. So to find the length, lambda is not given in the question. So we need to find lambda using some other way. We know that speed v is f times lambda. Also, the speed of sound in air is a known value, which is 343. So we use that. 343 is equal to the frequency, which is 514.5 times lambda, and we can plug 4L over 3 here. So L equals to 3 times 343 divided by 4 times 514.5. So L equals to 0.5 meters. Now to find the fundamental mode, we can use the formula for a tube closed at one end. The F1 is V over 4L. So V is 343 because that's the speed of sound in air, and divided by 4L, so 4 times 0.5 equals to 171.5 Hertz.